What is up, young chemists? Mr. Rosen here. How's it going? Hope you're doing well. This video is about molecular geometry, and that really just means shapes of molecules, and polarity. Okay, now, polarity is when you have a more positive region on a molecule as well as a more negative region on a molecule. So you have a region that's more positively charged and a region that's more negatively charged, and that can lead to different physical properties, like things like boiling point, melting point, vapor pressure. These are all related to the polarity of molecules because polarity of molecules plays a role in the what are called intermolecular forces, the attractive forces between molecules. So we'll start by thinking about the shape of molecules. Now, if you haven't watched the Lewis structure video, I recommend you go back and watch the Lewis structure video because we're going to be actually using those same Lewis structures as our starting point for this video. And I'll be writing the Lewis structures, but I'll be doing it quickly. I won't be explaining it. So if you want an explanation, you should go watch that video. So what it says here is when atoms bond to form a molecule, the bond is a region of space between the two atoms where you have shared electrons, right? And we usually represent that by drawing a straight line, but a single bond, which is a straight line, is a pair of shared electrons. You could have a double bond or a triple bond. Either way, the area between the two atoms contains a high concentration of electrons. We call the region an electron domain. Okay, now an electron domain could be a single bond, or a double bond, or a triple bond, or it could be a lone pair of electrons, meaning a non-bonding pair of electrons. Any of those would be considered one electron domain. Now, electrons have a negative charge, okay, and like charges repel, opposite charges attract. So the negatively charged regions where you have shared electrons will repel other electron domains. The electron domains will get as far apart around the central atom as possible. That's a key idea. This is called valence shell electron pair repulsion, or VESPER theory for short. This is the main concept or central concept for predicting the shape that a molecule will have. So here's an example, CO2. And if you want to know what the shape will be, you actually have to draw the Lewis structure and then look at the domains. So carbon is in column 4A on the periodic table, so it has 4 valence electrons. Oxygen is in column 6A on the periodic table, so it has 6 valence electrons, and there are 2 of them. So 6 times 2 is 12, plus 4 is 16 electrons. Okay. So now I'm going to draw the Lewis structure for it. I have carbon, and then I have an oxygen and another oxygen. Now you can start by connecting them with single bonds, and that will use up, that's 2 electrons and that's 2 electrons, so that would use up 4 of these and leave you with 12. And you would then have 12 electrons, and you need to have octets on all of these. And hopefully you recognize if you only have 12 electrons left, you could put 6 here and you could put 6 here, and your oxygens would have octets, but carbon would only have 4. So no matter how you arrange, if you're arranging those 12 electrons just as lone pairs, you're never going to satisfy all of your octets. The way to do that is to have more than a single bond. You can have double bonds here, and then add some lone pairs to your oxygens. Now, if you look at this, oxygen has 2, 4, 6, 8, carbon has 2, 4, 6, 8, oxygen has 2, 4, 6, 8, so they all have 8, they all have octets, and this has a total of 2, 4, 6, 8, 10, 12, 14, 16. Da-da-da-da. This is a valid Lewis structure. Now, if you're trying to figure out what the shape of this molecule will be, you look at the central atom, and you see how many electron domains are around the central atom. Now, As we said earlier, an electron domain could be a single bond, it could be a double bond, it could be a triple bond, or it could be a lone pair, but it's all about the central atom. So this double bond, this is one electron domain. And this is another electron domain. So there are two electron domains around the central atom. Those two domains, right, they're going to get as far apart as possible because this is a region with a bunch of negatively charged electrons, and this is also a region with a bunch of negatively charged electrons. So they're going to repel each other. And as far apart as they can get is on opposite sides with 180-degree bond angles. This situation where you have 180-degree bond angles, this is a straight line. It's what's called linear. That's the shape of this molecule, linear. So here at the bottom it says there are more than 5 shapes outlined on than the ones outlined on the next page, but we're not going to learn them. So you, for our regular chemistry class, are responsible for knowing the 5 shapes on the next page. One of them is linear, which I just showed you an example of. We also have trigonal planar, tetrahedral, trigonal pyramid, or trigonal pyramidal, and then there's bent, or V-shaped. Now, in terms of being able to predict the shape, it's all about how many domains are around the central atom, and how can those domains get as far apart as possible. So, this page, I'm going to have to sort of zoom in and zoom out, or I might actually, I'll probably just do it in sections. It has 5 cases. Each case is a shape. And it says number of domains. This is number of domains around the central atom. And then of those domains, how many of them are bonding. So in the example on the last page, our central atom had 2 domains around it. And both of those domains were bonding. So this case right here, we have 2 domains. We are 2 bonds. The domains are going to get as far apart as possible, which is linear. The bond angle is 180 degrees. And the shape of the molecule is what's called linear. This is a sort of partial Lewis structure, just showing the general shape of the Lewis structure. And even though these are single bonds, doesn't really matter. That's the general shape, right? Linear. And here is the ball and stick model, kind of gives you a little bit of a better idea about 3 dimensions. Just a straight line. So we have other situations, like we could have, what if we have a third domain, right? A third domain is going to make it so that, like, if we had this right here and we added another domain to it, you wouldn't maintain 90-degree angles. Those 3 domains would get as far apart as possible, like this, and as far apart as possible. This bond angle right here is 120 degrees, right? Because if you did 120 times 3, you get 360. This is what's called trigonal planar, when you have 3 domains and they're all bonding. Those 3 domains are getting as far apart as possible. And trigonal planar looks like this. You have a central atom connected to 3 things, and depending on how you view it, those 3 are flat. So you could actually turn it this way, and it would be flat on the page. Now, if you added another domain to this, if you were drawing a Lewis structure, often it looks like this on the page if you're just drawing it sort of casually. But this looks like you have 90-degree bond angles. Looks like it's flat, like a plus sign on the page. But if you're in 3 dimensions, these 4 domains can actually get farther apart in space than 90 degrees. They can get 109.5 degrees apart, which is a shape called tetrahedral. And if you look at this, hopefully that gives you a little bit of a better idea. You have a central atom and there are 4 domains. They are as far apart as possible. And if you look here at this bond angle, that's more than 90 degrees. That's about 109.5 degrees. And that's true for this one down here too. So these 4 domains are getting as far apart as possible. Drawing it flat on a piece of paper like this makes it look like a plus sign, like it has 90-degree bond angles, but it doesn't. Okay, so a way to draw, a Lewis structure like this with a little bit more 3 dimension would be you have something like B as your central atom, right? You have A, and then you have A. So those are like on the plane of the page. And then you have 1 coming out towards you, and they'll draw it with a solid wedge. This one is like coming out of the page towards you, and then this one, dotted line, is going back into the page. So obviously, I'm not an artist here, but the bottom is supposed to look like a little 3-sided pyramid standing up, and then you have a 4th domain sticking straight up. Okay, so this 3 is forming like the little triangle base, and then there's another domain sticking up. That would be a little bit of a better representation than a flat plus sign, and your bond angle is supposed to be about 109.5. Okay, now you could have 4 domains where only 3 of them are bonding, which would mean that you have a central atom here. This is 1, 2, 3, 4 domains, but only 3 of the 4 are bonding. So instead of having 3 domains where they're all bonding like this, which is trigonal planar, you have trigonal planar, which is flat, but then you have a non-bonding pair placed right on the center, and that's going to repel the other ones down. And so they end up standing up like a 3-sided pyramid. Or, 3 legs on the pyramid, I guess. This is called trigonal pyramid or trigonal pyramidal. And in this one, this right here, it's actually not really a bond. This is just a lone pair. And it's also represented sort of using like a paddle that kind of looks like that. And same thing here. These are not bonds. These are just lone pairs of electrons. Okay. If you have 4 domains and 2 of them are bonding, you still have 4 domains, so they're going to still get as far apart as possible, 109.5-degree bond angles. But 2 of them are bonding and 2 of them are lone pairs. So this shape is called bent or V-shaped. Central atom has 4 domains, 2 of them are bonding, 2 are lone pairs. Water is an example of this. So you have this in your packet. It's this page, this summary table of electron domain and geometry. This page is really, it's your one-stop shop, all things shapes of molecules. Okay, and I will be referring back to this throughout our video, but make sure you find it and you'll be using it. I have an ice cream truck that's driving by right now, and all my windows are closed, but it's still very loud. So if you can hear the ice cream truck, my apologies. Okay, so it says example problems and solutions. If you look at these molecules, you might recognize them from our last video on Lewis structures. These are all the same molecules that we already drew Lewis structures for. So I'm just going to redraw them, and I'll do that pretty quickly, but I want you to predict what the shape around the central atom is. So I'm going to draw the molecules pretty quick. Okay, we have F bonded to F with lone pairs around it. We have H bonded to I, which has lone pairs around it. We have GE, which is bonded to 4 H's. And we have H2O. I'll write these as well. Now again, if you're looking at these Lewis structures and you're like, how the heck is he doing that? Where is he getting those answers from? You just need to go back and watch the Lewis structure video because I work these out step by step and explain how to do it. So I'll just pause for a second. These are the Lewis structures. I want you to say what the shape of the molecule is. Okay? And you can, if you have your packet with you, you can find your summary table of your own. Okay, well, you always focus on the central atom. And in a molecule like this, there are only two atoms. So there is no central atom. There are just two things connected to each other. And if you have two things connected to each other, they have to form a straight line. Okay, they have to form a straight line. So if it's just two things, the shape has to be linear. Same thing with here. You just have two things, so it has to be linear. They're just connected by a bond, straight line. If you look here, the central atom has 1, 2, 3, 4 domains. Okay, 4 domains. And of those domains, how many are bonding? 1, 2, 3, 4. All 4 are bonding. Okay, so on our table here, number of domains, 4. Number of bonds, 4. So we have 4 domains and 4 bonds. Does our Lewis structure kind of look like this? Yes, it looks exactly like that. We just have a GE here and then H is on the outside. The shape is called tetrahedral. So we're going to write tetrahedral. For this one, I sort of intentionally drew it this way on the page, but if you look at the central atom, how many domains does it have? 1, 2, 3, 4 domains. Okay, it has 4 domains, and of those 4 domains, how many of them are bonding? 2 are bonding, 2 are lone pairs, 2 are non-bonding. So, looking at our chart, number of domains is 4. Number of bonds, not 4, not 3, but right here, 2. 4 domains and 2 bonds. If we go over this way, does our Lewis structure look like this? Sort of, right? I drew it a little different, but we have a central atom that has 2 bonds and 2 lone pairs. That's called bent or V-shaped. So the geometry is bent. You could also write V-shaped. And even though I drew it like this, maybe a more accurate representation would be you have H bonded to O with lone pairs bonded to H. Right? That's sort of more of a bent shape. This only makes sense if you're looking at it, right? If this was your bent molecule and then you were to rotate it and look at it from underneath, right? Then it could kind of look like a straight line, but if you look at it from the side, it will be bent. Okay, next one. This is actually just like our example with CO2, but it's SiO2. The central atom has 2 domains, and both of them are bonding. 2 domains where they're both bonding, those 2 domains are going to get as far apart as possible. So this shape is called linear. Here we have a central atom, and it has 1, 2, 3 domains. All 3 of them are bonding. So we have 3 domains, all 3 are bonding. Going back to our handy dandy chart, number of domains, 3. Number of bonds, 3. They're going to get 120 degrees apart, and that shape is called trigonal planar. And our Lewis structure does look a lot like this. Okay, one of them is a double bond, but that doesn't matter, it's just a domain. So this is trigonal planar, flat, like a plane, like on a plane. Okay, so we have 4 more. They're the same Lewis structures that we did in our last video. And again, I'm going to draw them out pretty quick, and then I want you to write the shapes. This one was 18 plus 7 is 25 is 26. 2, 4, 6, 2, 4, 6, 18, 20, 22, 24, 26. Okay, so those are your Lewis structures. Okay, so if you look at number 7, you might think, all right, if I'm looking at this molecule, what's the central atom? Well, you actually have two central atoms. We have this nitrogen, and we also have this nitrogen. So when you have more than one central atom, you're going to state the shape around both of them. So this nitrogen has 1, 2, 3, 4 domains. And of those 4 domains, 3 are bonding. So looking on our chart, 4 domains with 3 bonds looks like this, right? And our nitrogen does look like that. It has 3 bonds with a lone pair. That's called trigonal pyramid. And if we look at the one right next to it, it has the exact same arrangement. 1, 2, 3, 4 domains with 3 bonds. So both of these, okay, you would say trigonal pyramid around both nitrogens. That's the shape around both of them. If they were different, you would say trigonal pyramid around nitrogen, and whatever. Trigonal planar around carbon, or whatever else would it be. So same sort of thinking applies here. You have 2 central atoms. The carbons are both central. And both carbons have 2 domains. This is one domain, and that's one domain. So remember, even though it's a triple bond, it's still just one domain. So this carbon has 2 domains, and they're both bonding, and this carbon has 2 domains, and they're both bonding. So it's straight line all the way across. It's linear around both carbons. So that's what you would write. Linear is the shape around this carbon. Linear is the shape around this carbon. So linear around both carbons. Oops, that's supposed to be there should be a bond between the P and the O here, which I drew, but it was cramped, so sorry about that. Okay, here we're looking at the central atom, chlorine. It has 1, 2, 3, 4 domains. Of those 4 domains, 3 of them are bonding. So 4 domains, 3 are bonding. That's what's called trigonal pyramid. Just like up here, right? This has 4 domains with 3 bonds. This also has 4 domains with 3 bonds. And here, our central atom, phosphorus, has 1, 2, 3, 4 domains. That's a bond right there. Sorry, they're kind of connected. But that's 4 domains and all 4 are bonding. When you have 4 domains and all 4 are bonding, that's called tetrahedral. So shapes, of course, just takes practice. You just, go back and forth with your little chart here. But pretty quickly, you sort of internalize and memorize these 5 shapes: linear, trigonal planar, tetrahedral, trigonal pyramid, and bent or V-shaped. And you'll get to know their bond angles. Now, the shape of the molecule is important because the next thing we're going to do is talk about the polarity of the molecule. And the polarity is influenced by the shape, and the polarity is going to have a big role in the intermolecular forces that exist between molecules within a sample of it. So here at the top, it talks a little bit about electronegativity, which I talked about in our Lewis structure video. But electronegativity is a measure of how strongly an atom will pull shared electrons towards itself. So if something has a higher electronegativity, it means it pulls shared electrons towards itself more than something that has a lower electronegativity. So here you have an example of HF. If you have H and it's bonded to F, that bond represents shared electrons. The electrons are in the space between these two atoms. Now, the general trend for electronegativity, okay, on the periodic table, just draw a mini periodic table here real quick. The general trend is, if that's our periodic table, these are the noble gases. They basically have, we ignore them in terms of electronegativity because they have full octets and they don't tend to pull shared electrons towards themselves. But in general, if you go up and to the right, electronegativity increases. That says increases. It's basically illegible, but fluorine is right here on the periodic table. So it's the most electronegative element. So that means these are shared electrons. They're not going to be shared equally between the two of them, right? If I had hydrogen sharing electrons with another hydrogen, this hydrogen would be pulling on these shared electrons, and this hydrogen would be pulling on these shared electrons. And because they're the same element, they have the same electronegativity, that's like a tug of war with me and my clone, right? Who's going to win? It's going to be a tie, right? They're going to end up sharing these equally. Whereas down here, fluorine has a higher electronegativity. So these shared electrons are going to be pulled towards the fluorine. And this is what's called a dipole arrow. I'll put a little tail on it here. This will become a more positive side, and this will become a more negative side because the electrons will be pulled over to this side. Electrons are negatively charged. So if negatively charged electrons are pulled over to one side, it creates what's called polarity on the bond. Polarity means opposite ends or extremes, like the north and south poles of the Earth, right? Polarity is caused by unequal sharing of electrons, which is due to electronegativity differences. If you get polarity on a bond, it creates a region that's more negatively charged and a region that's more positively charged. And positive and negative regions then interact with nearby molecules that have positive and negative regions, and opposites attract, and you start getting these stronger intermolecular forces, forces between molecules. Now, you can have polarity on a bond, and then you can have polarity on a whole molecule, right? And in this case, if this is the molecule and there's only one bond, this would be what's called a polar molecule, because the electrons are pulled to one side. To have polarity on a molecule, you need to have one side or region which is more negatively charged than another side or region, okay? So for these, and again, they're the same molecules, right? For this one, if you look at this and you think, okay, what is this, a polar molecule or nonpolar? Well, just like my example with hydrogen here, fluorine and fluorine, they're the same. So these shared electrons, they're not going to be pulled more to this side. They're not going to be pulled more to that side. They're going to be shared equally. So that means that this side of the molecule is the same as this side of the molecule. There's no difference, right? One region's not any more positive or negative than the other region. So that means it is non-polar, right? There's no difference in electronegativity, so the electrons are not pulled more to one side than the other. Okay. For Hi, this well, actually, I don't have a table with specific electronegativity values on it, but hydrogen has a value of about, the electronegativity values range from about 0.7 to about 4, which is fluorine, okay? Hydrogen is about a 2.1, and iodine is higher than that. Iodine's like right over here on the periodic table. So the electrons are going to be pulled more to this side. And you can see that just one side of this molecule is different than the other side. This side's going to be more negative. This side's going to be more positive. It's not, asymmetry is a big part of polarity. If it's totally symmetrical and the same on all sides, it tends to be nonpolar. Whereas if you have asymmetry in the molecule, one side's different than another side, you tend to get some polarity. Okay? So for this one, we have GE. Now, even, let's say we don't know the values of electronegativity here, but whether the electrons are getting pulled out towards the H or pulled in towards the G, over here you have the same element doing the same equal and opposite thing on all sides. So hopefully you see just in the symmetry of this molecule, one side is not going to be any different than any other side, right? And if another molecule were to approach this molecule from this side, or approach the molecule from this side, or from this side, it would not have a different experience. Okay, all of the sides would be the same. And because all of them would be the same, that is a nonpolar molecule. Okay, now H2O, we have hydrogen bonded to oxygen, which has lone pairs, and then we have hydrogen. Now, in terms of these shared electrons, oxygen has a higher electronegativity than hydrogen does. Okay, oxygen is right next to fluorine. It's one of the most electronegative elements. So these shared electrons are going to be pulled up towards the oxygen. And these shared electrons are going to be pulled up towards the oxygen. Now, if it was a linear molecule, those would be pointing right at each other, and they'd be sort of equal and opposite and cancel each other out. But the shape of the molecule is bent or V-shaped. So the electrons are actually getting pulled up this way, right? They're actually getting pulled up towards the oxygen, plus you have these lone pairs here. So the sort of net overall direction of polarity, is up. This is going to be a more negative region, and down here would be a more positive region. Water is a polar molecule. One side of water is more positively charged, and the other side of water is more negatively charged. This is hugely important, okay? The fact that water is not linear, but has a little bend to it, the fact that water is bent is responsible for all of life as we know it, okay? If water was a straight line, if it was linear, it would be nonpolar. And if it was nonpolar, water, when it comes in contact with another water molecule, it would not experience the same attractive forces. Okay, because right now, as it actually is a polar molecule, there's positive regions and negative regions. So when a water molecule interacts with another water molecule, the positive section of one is attracted to the negative section of the other, and they cling to each other. And they form these strong intermolecular attractive forces. And the fact that they cling to each other is why we have to get water so hot before it boils, because you have to heat it up, heat it up, heat it up until you can actually overcome those attractive forces. Okay? Other molecules its size go from a liquid to a gas at a much lower temperature because they're not held together as strongly. All right? We have liquid water here on Earth, liquid water through a temperature range, which is what we experience based on our distance from the sun. And if water didn't have this bend, none of it would be liquid at our conditions. It would all be gas. So the properties of the water, boiling point, melting point, vapor pressure, are related to the shape, and that shape plays a key role in the polarity of the molecule. Let's continue along. So these are the other 6. All right. We have SI. Shoot. I'm just going to redraw that. Sorry. I forgot the bonds. So I'm going to draw out. I'll just go ahead and draw out all of these real quick. This is in square brackets, sorry. Okay, I was just drawing these out again. All right, so predicting the polarity of the molecule. If you look at this, oxygen is more electronegative than silicon is, so these will be pulled out towards the oxygen somewhat, but this is a linear molecule, and on the opposite side you have the exact same thing happening. So kind of equal and opposite, yeah, the electrons are getting pulled out a little bit, right? My thumbs are kind of sticking out like that, okay? But they are equal and opposite and cancel each other out in a sense that, like, if you were to approach the molecule from this side, it would be no different than if you approach the molecule from this side, okay? And because of that, this is a nonpolar molecule. If we're looking at this molecule right here, carbon has a higher electronegativity than hydrogen, so these are it's not a big difference, it's a pretty small difference actually. Hydrogen's 2.1 and carbon's 2.5 approximately, but shared electrons will be pulled in a little bit. Oxygen is more electronegative than carbon, so these are pulled this way. And if you look at the sum of your dipole arrows, right, this is going this way, the other one is also going this way, and then from carbon to oxygen, it's going that way, okay? So if you add these all up, the overall direction is to the right, right? This region over here is going to be more negatively charged, and this region over here is going to be more positively charged. One side is distinctly different than the other side, right? If I approach the molecule from over here, it'd be way different than if I approach the molecule from over here. This is a polar molecule. For this next one, the shape is trigonal pyramid on all three, and trigonal pyramid is sort of like this. So I know that when I draw this on the Lewis structure, this will be going in, this will be going in, and then you have a lone pair. And the same thing is happening over here. For these, I know it looks like they're at 90-degree angles, but it's sort of like this, and they're going towards the nitrogen on both of these, and then you have this lone pair. This region is going to be more negative. Okay, and I mean, you're gonna get some polarity probably on this molecule, but not much, because it really is the same on both sides. But maybe in the region around the nitrogen, you could get some. So this is maybe not our best, clearest example, but I'd say probably you'll get a little bit of polarity rather than totally nonpolar, but not much. So it is a continuum. So, it ranges from nonpolar to very polar, or all the way to what's called ionic. But if you have a difference in electronegativity of more than maybe 0.5, you get some polarity on the bond. For this molecule, there's no difference between these two carbons, and you can see there's a Br on both sides. So Br is going to be a little bit more electronegative than carbon is. Well, they actually might be, again, very similar in electronegativities. Almost no difference in electronegativity. So not only is there very little difference in electronegativity between these, but it's the same on both sides. So one side's no different than the other side. We have that symmetry. This would be more of a nonpolar molecule. Now, for number 9, if this didn't have this lone pair right here, then it would be trigonal planar, and all three would be the same, and it would be nonpolar. But the fact that it has that lone pair means instead of being trigonal planar flat, it's up. It's standing up like this, like a pyramid. And so for each of these, there is an arrow moving, and in this case, it's going out towards the oxygens on each side. This is going to give you some polarity on the molecule. And in general, when you have a trigonal pyramid shape, you're going to get some asymmetry and just inherent in the shape. Okay? And because you have some electrons, if you have a molecule that's shaped like this, approaching, from this side where my fingertip is an oxygen, if I approach it from here, that's going to be a radically different experience than if I approach it from this side, which is just a single chlorine. Okay, so just inherent in the shape of trigonal pyramid is some asymmetry and therefore some polarity. In contrast, this phosphorus has 4 domains around it. All 4 domains are bonding, and they are all bonding to oxygen. So while, yes, there is some electronegativity difference going out towards the oxygen, the exact same thing is happening in the opposite direction up above and left and right in all sides. And hopefully you can see that if you approach this molecule from any side, it would be the same experience, and overall, this is a nonpolar molecule. Okay? If you have a tetrahedral shape where all 4 things are the same, it's going to be a nonpolar molecule because one side is going to be no different than the other. All right? So identifying if it's a polar molecule or not is a challenging thing, but to do it, you have to be able to predict the shape of the molecule beforehand. And the way to predict the shape of the molecule is to draw a valid Lewis structure. And you can see how the chemistry is building on itself at this point. So in this video, we practiced not only a little bit of review in terms of how to draw a Lewis structure, but we then looked at those Lewis structures and figured out what the shape of the molecule is. That's called the molecular geometry. There are 5 shapes you need to know: linear, trigonal planar, tetrahedral, trigonal pyramid, and bent, or V-shaped. We then, based on the Lewis structure and based on the shape of the molecule, predicted if it was a polar molecule or not. If the molecule is polar, it's going to have a positive region and a negative region. And those oppositely charged regions will attract other nearby molecules and cause the molecules to cling together, and that will lead to increased surface tension, higher boiling points, higher melting points, lower vapor pressure. These are all important physical properties of the substance which play a big role in what we experience in our everyday life. And we'll learn more about those intermolecular forces later in the year. As always, keep up the good work. Let me know if you have any questions. This is Mr. Rosen. Out.